By the time we're done with this video, you're going to be able to do great on all of these different rules of exponents. I want to go ahead and start off with the multiplication rule. Here's an example of the multiplication rule. So we might have something like a to the third power times a to the second power. Now these powers literally mean how many are being multiplied. So a to the third is really 1, 2, 3 a's, and then a squared is 1, 2 a's. But this is why we need these properties. These are nice small numbers. I can just count these a's up and I've got 1, 2, 3, 4, 5 of them. So this is equal to a to the fifth. Or I could use my property that says you can just add your two exponents together. So my base here is a. I've got 3 plus 2 being multiplied, which gives me a to the fifth. So here's our multiplication rule. A to the m, so just some power, times a to the n. As long as you have the same base, in this case it's a, you can add those two exponents or powers together. So this is equal to a to the m plus n. Next up is our division rule, and we're going to start again with a really simple example. Let's do this one. Let's do a to the fifth divided by a squared. So in this case, I've written it as a fraction, and I literally have 5 a's in the numerator. Now again, these rules are going to keep you from having to do this expanded form every single time. In the denominator, I've got 2 a's being multiplied. So there are my 2 a's being multiplied. Now I can go ahead and reduce this. I can cancel. I've got an a here, numerator and denominator. I can cancel those. There's another a, numerator and denominator, which leaves me with 3 a's. So the exponent of my answer here would be an a cubed. Or I can notice that this happens to be the difference between my two exponents. So this would be a to the 5 minus 2. So here comes our rule when we're doing a division of the same base. So we could say that a to the m divided by a to the n is equal to, as long as it's the same base, you're going to take that top exponent and subtract the bottom exponent a to the m minus n. Next up is our power rule. I like to think of this one as power of a power rule. So as I put this one together, I'm going to take a squared and I'm going to raise this entire quantity to the third power. Now again, this power 3 literally means that we've got 3 of what's in parentheses. So I can rewrite this out as a squared, a squared, a squared. Okay, so again, I'm just going to do this once, but you could write this out as double a's in each of those parentheses and then count them all up. If I count all of those up, there are 6 of them. So this is a to the 6th power. But I can also notice that a to the 6th would be the product of the 2 times the 3. This is why I really like power of a power, because of in math means to multiply. So we could have also tackled this one by multiplying those 2 powers together, a to the 2 times 3. So if I were to write my rule out for this one, I would write it out as a to the m, all raised to the n power. I multiply those 2 powers together. So this is equal to a to the m times n. Next up is 0 as an exponent. So we want to decide what a to the 0 power is. And I'm going to take that definition of a power super literally as we come up with what a to the 0 is. We're going to establish a pattern, and this is what I love about math. Everything is super well defined. So I know that a cubed would be 3 a's being multiplied. A squared would be 2 a's being multiplied. A to the first power would be a single a being multiplied. But if I were to take a close look at each of these, I have a times a times a. I could also put a little 1 in all of those, like as the coefficient out in front. So I've got 1 times a times a times a. It means exactly the same thing. This would be 1 times a times a, 1 times a. So when I look at that a to the 0 power, so a to the 0 power, there are 0 a's being multiplied, but I still have that coefficient of 1. I can write that coefficient of 1 out here in the front, 1 times a to the 0. There aren't any a's being multiplied, so I do have the 1 left. Okay, so what does this rule look like? This is an important one to have memorized, but here's our rule. A to the 0 power is equal to 1. Next up are negative exponents. So what do we mean when we say something like a to the negative 2? You want to think about this as really living in a fraction. So I'm going to think of this a to the negative 2 as an a to the negative 2 divided by 1. That negative 2 power is really telling me, well, two things, that I've got 2 of something. But the negative in particular is telling me that this lives, my base, lives in the wrong spot in my fraction. So it's a reciprocal rule. So as I apply the negative sign, it tells me that the a squared lives in my denominator. So let's go ahead and put the a squared in my denominator, and we're going to put that 1 there as a placeholder in my numerator. But what does this look like if I had, say, 1 over a to the negative 3? That negative sign tells me that it is in, and when I say it, a cubed is in the wrong spot in my fraction. So I want to move it from my denominator up to my numerator. So applying that negative sign, I'm going to rewrite this fraction, and I'm going to move the a cubed. I've applied the negative for the power. So now I've got a positive power 3 in the numerator and a 1 in the denominator. So this is going to give us really two versions of this rule. So as I put this rule together, I'm going to write it in two ways. So I'm going to write it as an a to the negative n is equal to 1 over a to the n, but I'm also going to write it the second form that we worked with, and that was a 1 over a to the negative n. And that brings it up into my numerator, so this is equal to a to the n. So those negative powers move the base to the other part of the fraction. We're already at number 6. Number 6 is power of a product. Let's do an example, and I'm going to do one that's fairly easy to work with. So I'm going to do an a cubed times a b squared, and we're going to do this all to the second power. So I've got my product there in the parentheses to the power 2. Now I can go through and expand everything, right? This literally means that I've got 2 of everybody. So this literally means I've got an a cubed b squared and an a cubed b squared. And then using the property that we saw before, I can go ahead and count up how many are being multiplied. Let's do the a's first. So for the a's, I can go ahead and combine those. They are really being multiplied. They're part of this multiplication. So I can add those exponents together. So that would be a to the 3 plus 3. And doing something really similar now for the b's. The b's are also being multiplied. So using the multiplication rule that we saw earlier, this would be b to the 2 plus 2. And that makes our answer a to the 6th, b to the 4th. But knowing this rule is going to make this one easier than what I just showed you. So here's that rule. So that rule says if I've got a product, so let's do a to the x and then b to the y, and I'm going to raise all of that to the nth power. Instead of expanding it like I did here, I can just bring the power inside. These now become powers of powers. So I'm going to take that a to the x. It is raised to the nth power. Same with the b to the y, also raised to the nth power. These are powers of powers. So we end up with an a to the xn times b to the yn. Similarly, we can do a power of a quotient. I'm going to start with the rule this time, and then we'll do an example. So our rule looks like this: a to the x divided by b to the y, all to the nth power, is equal to, I can also distribute that nth power. As long as it's a division or a multiplication, I can take everything to the nth power. So this is going to look like a to the x times n divided by b to the y times n. Here comes an example. So in this example, I'm going to take, let's do an a to the 4th divided by b to the 5th, and I'm going to take this all to the 3rd power. All I've got to do is to apply the power to the numerator and apply the power to the denominator. Doing that, we get an a to the 4th times 3, or you can just do the multiplication in your head, and then a b to the 5th times 3. And then simplifying, that becomes an a to the 12th divided by b to the 15th. We've got one more rule to go. The last rule is rational exponents, and rational exponents or fractional exponents turn something that is in exponent form. So if I do a to the 2/3 power, it turns it into a radical. And when I'm turning it into a radical, whatever my denominator is the index or the type of root. Whatever my numerator is I just call it the power. It's just like my normal power. So when I put this together, my index or the type of root is a cube root, and the power on that same base a is squared, so a squared. I can write that out as a rule. So a to the m divided by n is equal to, n is the type of root, so this is going to be the nth root, a to the mth power. A really common example of this would be an a to the 1/2 power. Now that 1/2 power gives me two pieces of information. The 2 is the type of root, so if I write this using my formula, I get the second root, and then the power is the numerator, so that's going to be an a to the 1st. But I know that the second root is really just the square root, and a to the 1st power is equal to a. You got through all of them. You're doing an amazing job with exponents.